Hello. Today we'll continue where we stopped off, and we're talking about three-dimensional shapes. And in today's lecture, our conversation, our talk will hinge on finding total surface areas of three-dimensional shapes. Now, on the picture, you see I've actually extracted this from your learning guide, which is on page 75 of your learning guide. You see two sets of three-dimensional shapes. The first set is made up of the prisms, which is the triangular prism, square prism. Again, as we discussed last time, the names of the shapes are derived from the bases that they are made of. The first one being a triangular prism because the base is a triangle. The other one being a square prism because the base is a square. Rectangular prism, pentagonal prism, hexagonal, and octagonal. So that's that for the prisms, and also the pyramids are also named after the bases. So the first one being a triangular pyramid because the base is a triangle. The other one is being a square pyramid because the base is a square, up to the last one, which is an octagonal pyramid because the base is an octagon, which is made up of 8 sides. Now, all these shapes, their bases are regular, meaning the sides, the lengths of each edge, the edges are equal. They are regular shapes. Now, let's move on then to what we're going to talk about today, which is how do we find the total surface areas of these particular three-dimensional shapes. First, let's start with prisms. With the prisms then, we'll start by looking at a triangular prism. Let me start with a square prism. A square prism would have that square, the front part. It would have that square, and maybe the other square would be here, like that. And if we were to join that, this would be our square prism, these being squares and the rest being rectangles. Now, if we're to find the total surface area of this, the first thing we'd have to do is to show our children, again, like I insisted last time, when you are teaching shapes, the topic of shapes actually is a very practical topic. Insist on your children bringing the actual shapes to class. Tell them, tomorrow we'll be dealing with cuboids. Each one of you bring your own cuboids from home. They will look for boxes and all kinds, and they'll bring them to class, and you'll be amazed at how much they can learn from their own teaching aids compared to the ones that you provide yourself. So take advantage of your children's resources. They are always very resourceful. And they are usually helped by their parents and their siblings as well. So let each child have a shape like that, and then you tell them to open it up at the edges. So this would have that would have the other one square there, and the other square would be there. Then the other rectangles, there would be a rectangle there, and there would be another rectangle there. And if it is closed at the top, there will be the fourth rectangle. So these are rectangles, and these are the two squares. So the total surface area, therefore, we're talking about is the area that this prism square, the area that this square prism would occupy if it was opened up on a flat surface. So it is that area. This is what represents what we mean by a total surface area. That is the area we're looking for. Now, there are formulas in mathematics that we follow. For instance, we know the area of a square is given by length multiplied by the length. So it would be this length multiplied by that length. The area of a rectangle, for instance, this rectangle, would be this length, which would be a different L. Maybe let this be small l. Let that be small l multiplied by the breadth. So, total surface area is, we have two squares, so it will be 2L times L. Why? Because there are two squares. Plus, the area of this rectangle is length times breadth. But how many do we have? There are 4 of them. Therefore, we can multiply this by 4 times 4. That provides us with a total surface area of that square prism, the area it would occupy if it was opened up. Let us look at another prism. For instance, this time, let us look at a triangular prism. So let's draw one. If we were to draw a triangular prism, connect that. Oh, this is horrible. Let's redraw that. That's much better. And connect that to that, that to that, and that to that. So there's my triangular prism. Again, the name being derived from the base, triangular prism. Now, if I'm asked to find the total surface area of this, I would open it up. And I would have the first rectangle, the other rectangle, the other rectangle. Again, this would be good exercise with your children. Let them do this. And if they are able to see the various parts that their shapes are made up of, that enables them to understand what you mean by the total surface area. They are therefore able to see that in actual fact there is a triangle here and there is another triangle there. There is that rectangle, that other rectangle, and that other rectangle. So, it's this triangle and that triangle, plus the 3 rectangle. So it's that, rather, did I say rectangle for that? No. This triangle, it would be this triangle plus that triangle plus the 3 rectangles. So that provides us with what the total surface area for this would be. So SA, therefore, would be equal to, now we know the formula for area of a triangle is given by half the base multiplied by the perpendicular height. Now, the perpendicular height for this triangle would be that. It's the height that is at 90 degrees to the base. It's that. So that would be the perpendicular height we're referring to here. And it's very important for children to see that. And that would be the base. But how many of these triangles do we have? There are 2 of them. So we would multiply that area by 2 plus L times B, which would be the area of the rectangle. But how many do we have? There are 1, 2, 3 such rectangles. Therefore, the total surface area for our triangular prism would be 2 times half the base multiplied by the height plus 3 times the length times breadth of the 3 rectangles. So that's how we would would find the area. And then if the dimensions were given, would plug them in and find our answer that easily, I hope. Now, some of the questions that are a little bit difficult on this topic is something that probably they begin to do in round about, say, grade 4 or 5, and you are required to know that even if you are elementary and foundation phase teachers, because such relatively advanced knowledge is critical for you, because once you have that, you'll be able to explain these concepts much better to grade 1, grade 2, or even foundation phase children. So let's look at a slightly harder question then that would come out of this. Let us say this time we're dealing with a hexagonal prism. That would mean it's a hexagon. So if it's a hexagon, it would have 6 sides. Now, in most cases, the questions that are asked refer to regular. Regular means all the sides of the hexagon are equal. Now, if it's hexagonal, would have another hexagonal face like that, and would then connect these sides like that, and that would be our hexagon that way. So the question would be, in most cases, again, we ought to remember this, it is possible for us to find area of a hexagon if we were given the dimensions correctly. We can find the area of the hexagon if we're given the dimension correctly. For instance, we may divide it into the various parts that it is made up of, which are 1, 2, 3, 4. 4 triangles. 1, 2, 3, 4 triangles. And if we are given the dimensions and so on, we'll be able to find the area of this and therefore use that to find the total surface area. However, in most cases, the area of this would be provided. The area of the hexagon, of the regular hexagon, would be provided. So let us say this time that the area is provided. So let's remove that. So we are told that find the area, find the total surface area, find the total surface area of a hexagonal, find the total surface area of a hexagonal prism given the face of the prism So then find the total surface area of a hexagonal prism given the face of the prism, or it would be given the area of the face of the prism to be, say, 100 centimeters squared. So what it means is that we must therefore open this prism up. Now, since it's a hexagon and it is regular, we are told would be given the area of a regular hexagonal prism. So if it is regular, that means all the sides are equal. That side, that side, that side, that side, that side. All these sides are equal. Now, and that would be one face. That would be the other face, the bottom face, and the side face. So since it's a hexagon, that means it is going to have 6 rectangles. It's going to have 6 rectangles. If we opened it up, there would be one rectangle followed by another rectangle. That's 3, 4, 5, 6. Now the hexagon therefore continues that way, and the other face would be that side, like that. So these would be the hexagons that make up the hexagonal prism when it is opened up. Now, we already, first let's look at the question. It's find the total surface area. That's what the question is. So that means we must find the area of this hexagon and the area of that plus the area of the 6 rectangles. However, now, if we have to find the area of the rectangle, it means we need to know its length and its breadth. But the breadth is the same as the side of the hexagon, because these rectangles make up the parts of the hexagon. So if we were told then that that side there was, say, 5 centimeters, and the length from that to there was 10 centimeters, that would mean for this rectangle, the area would be length multiplied by the breadth, which would be 10 centimeters multiplied by 5 centimeters, which would give us 50 centimeters squared. Now, that is area for one. That is area for one rectangle. But how many rectangles do we have? 1, 2, 3, 4, 5, 6. Why? Because it is a regular hexagonal prism. Therefore, each rectangle will be equal to the other rectangle. Why? Because they are regular. The lengths are the same, and the sides are the same because it is a regular hexagon. So, would therefore, if that is the area of one rectangle, for 6 of them, would multiply that by 6, which gives us 300 centimeters squared. But that is only area of the total surface area of the 6 rectangles. We were told in the question that the area of the hexagonal face is 100 centimeters squared. So, since there are 2 such faces, that would be 200 centimeters. So, plus 200, this gives us 500 centimeters squared, would be the total surface area of this hexagonal face. Is that making sense to everyone? Now, what we have to remember here, however, is that not all the time will the faces be provided. Sometimes this might be a shape whose face, frontal face, is not there. In other words, it is an open hexagonal shape. So if it is open, it means that this part is not there. These parts are not there. It is only that the hexagon only helped us to shape our figure. That means, therefore, the total surface area of this, because it is open, would only be 10 multiplied by 5, which is 50 for 1, multiplied by 6, which would be 300 centimeters squared only. Why? Because it is open on both sides. But what if it was open probably at the top and closed at the bottom? That would mean the bottom part would be like that. So we would still have that area there. So it would be the area of the six rectangles plus the area of just that one hexagonal face. So it would be 300 plus 100, therefore it would be 400 centimeters. Now, if it was closed on both sides, and that would also be the case. So that is just what we should remember whenever we are given such questions. And also now, when teaching this to our children, what is critical here is for them to actually see. In other words, you should be able to draw. You should be able to, let me erase that. You should be able to actually show them why the various parts of the hexagon. Now, let them practice drawing, but they must have the actual figures in front of them. Some of these shapes, especially the prisms and the pyramids, would not be easy to find. For instance, an octagonal prism, an octagonal pyramid. It might not be easy to find it. But if you can, bring them in class, let them see. And again, give them an opportunity to bring their own. As you break these shapes down, they would be able to see the various shapes that the octagon, 1, 2, 3, 4, the hexagonal, 1, 2, 3, 4, 5, 6. The other parts there, and the other parts there. How it is. So these make up the various parts that they should be able to open their own shape, see the rectangles, and so on. Now, this is what I would like you to hinge your conversation with your children on. And the most important part to emphasize here is that, one, it is regular. Now, if it was octagonal, that would mean it would have 8 sides, and again it would be regular. What's the difference between regular and irregular? An irregular one, the difference would be that if it was irregular, these sides would not be the same. What does that imply? It would mean that the rectangles that are provided will also not have the same areas. Not that they can't be mathematically be found, especially if we are given the dimensions. They can be, but at their level, we always assume, well, we would like them to easily calculate that. Though in actual fact, and again, remember, by them understanding this, these are the shapes that they'll be dealing with when they are now doing advanced mathematics, engineering, construction, This is what they'll be dealing with. And their understanding of these shapes and how they are made and so on from elementary level enables them to understand the mathematics at a later stage. Therefore, I was trying to explain the difference between a regular and an irregular. An irregular octagon, for instance, so this was going to have 8 rectangles. Now, if they were irregular, that would mean these dimensions here, that would not be the same as that. That would probably be shorter. That means that rectangle would not be the same as that rectangle. Then that would be provided by that, and that would be that. If that was also different, that would mean that side would be different from that side. So the area of this rectangle would not be the same as the area of that rectangle. Why? Because we have an irregular octagon, and these sides make up the bases of the rectangular of the rectangles that form the octagon. So and again, it's important for us to explain that, because children need to know, why are we talking about regular and irregular? And you should be able to explain that. And if these lengths were provided, if the lengths were the same, it is also still possible for us to find the total surface area, even if they're irregular, because we would know the length of that multiplied by that. And we would know the length of that multiplied by that. So we would know the area of that rectangle, and would also know the area of that rectangle. So we would add these two. However, our problem would be finding, which wouldn't be problematic really if we knew the dimensions, would be able to find now the area of the octagon, that by creating those various triangles like that. This is actually still a hexagon, but if it was an octagon, it would be 8. So let us insist on it being a hexagon. Let me erase the other two, so that we're still dealing with a hexagon. So we're still dealing with a hexagon, but irregular. So the area of this triangle here would not be the same as the area of that triangle, which would be able to find as long as we know the perpendicular height there. And we also know the perpendicular height of that one, but that area would not be the same, because that dimension there is not the same as that one there. So these triangles, therefore, 1, 2, 3, 4, 5, 6 of them, would provide me with different areas, which I would add to my different areas of the rectangles. And I would still be able to find the total surface area of my irregular hexagonal prism. So here, therefore, what we are required to know is, 1, we need to know the knowledge of finding area of a triangle, which is half the base multiplied by the height. But this is area of a right-angled triangle. Area of a right-angled triangle. But for a non-right-angled triangle, for instance, one that was maybe like that, would still know, would have to know that height, that perpendicular height. For a right-angled triangle, that would be perpendicular height, and that would be the base. For a non-right-angled triangle, that would still be the base. Now look, the base goes beyond further. Would still be that base multiplied by the perpendicular height, and this would be that base multiplied by the perpendicular height. And if we do not know this, we should be able again to use Pythagoras' theorem, which is to find the area of that, A, B, C, for instance. A squared is equal to B squared plus C squared. And that should enable us to find the height if we know the part of the base and the hypotenuse. So Pythagoras' theorem, A squared is equal to B squared plus C squared. That would enable us to find that. So I think, so that's the knowledge of area of a triangle therefore becomes critical. That is, if it has not been provided. But in most cases, the area of either the octagonal shape, the pentagonal shape, so the frontal part, the area of the frontal part is usually given, and the children would probably be asked to find the total surface area and add the frontal part to it. So that is it really that we ought to know about this part of surface area. In our next lecture, we'll talk about the total surface area of pyramids, and these were regular prisms. We'll talk about regular pyramids. Otherwise, have a good day.